In this video, we'll be covering implant-associated tumorigenesis. The learning objectives of this video are to recognize the risk of implant-associated tumorigenesis, to understand the concept of chemical carcinogenesis, and to understand the concept of foreign body carcinogenesis. So we've shown this slide before about the host response and appropriateness of different responses, but now we're to the last response on our list here, which is of course never appropriate, and that is tumor formation. Before we jump into the mechanisms though, we have to define a few concepts related to tumorigenesis. So first, benign tumors are tumors that do not invade adjacent tissues or spread to distant sites, whereas malignant tumors do invade surrounding tissues and gain entry into the lymph and blood vessels, and that facilitates their metastasis to different sites. A carcinogen is a compound that acts as a stimulus to cause malignant transformations, and it's thought to occur due to mutations in the DNA of normal cells, and that process is known as mutagenesis. So when we get to testing later on, we'll talk about a test method for assessing mutagenicity. And then in terms of carcinogens, we also have three different subterms here. So a complete carcinogen is a compound that causes this malignant transformation by itself. A procarcinogen is not a carcinogen in its native form, but it can be converted to one by metabolic processes. So in metabolism, enzymes act on molecules and they change the functional groups that are present, so they slightly change their composition, and it can convert a procarcinogen to a carcinogen. And then lastly, a co-carcinogen does not possess any inherent mutagenic potential on its own, but it enhances the activity of others, so it's kind of like a cofactor for carcinogenesis. Now let's talk about the stages of tumorigenesis. So an important point is that even in the presence of a carcinogen, the malignant transformation is often a result of an accumulation of genetic damage. So it's not just one mutation oftentimes. So therefore, it's a multi-step process. There's an initiation phase, which is where you have a primary cellular transformation. So later on, we'll use the term pre-neoplastic. So the cells at this stage, they haven't turned into tumor cells, so we call them pre-neoplastic cells. This phase is followed by a latency phase, where there's no visible tumor formation, and this can last for many, many years, so on the order of 15 to 20 years for humans. And then finally, we have the promotion stage, where you actually get tumor development and growth, and it can be visually observed. So this figure kind of describes this process graphically. So again, we have the initiation phase, and this is the transformation of the DNA. So that's the mutation step. This initiation phase is followed by the latency phase, which is variable in length, but in humans it can be many, many years. And then finally, we have the promotion stage, where you have tumor growth around the implant, as is shown up above. Now, the initiation step or phase can happen two different ways. So one option, so I'll label it as an A here, is chemical carcinogenesis. The second option, B, is foreign body carcinogenesis. So now let's talk about these two processes in a bit more detail. So chemical carcinogenesis is caused by substances leaching out of the implant. So these are mutagenic compounds. So this can be things like monomer, initiator, or solvent, if we're talking about polymers, or in the case of metals, it could be metal ions associated with corrosion. And now these aren't all-inclusive things here, so there could be other mutagenic compounds as well, but the key point is that they're mutagenic substances leaching out of the implant. On the other hand, foreign body carcinogenesis happens when there is no chemical carcinogenic activity. So there's nothing leaching out of the implant that's mutagenic, and yet we still get tumor formation. So in rodents, it's been observed that this the tendency or the ability of a material to cause a malignant transformation increases with implant size, but the exact cause of foreign body carcinogenesis remains unclear. But it is thought that it's due to changes in the local environment. So these changes, and then also if we think about the effects of implant size that have been observed, suggest that it's related to the foreign body response that we've learned about before, and hence the name foreign body carcinogenesis. So things that matter in terms of the tendency for foreign body tumorigenesis and things that can contribute to it are the bulk properties of the implant, physicochemical surface properties of the implant, and then local tissue damage leading to insufficient nutrient exchange and disturbed cellular growth around the implant, and the interruption of cellular communication. All those things are related to the foreign body response. And so if you think about bulk properties of the implant or the physicochemical surface properties, we know from before that those things can affect the extent of the foreign body reaction. And just like we know a larger implant is going to cause more inflammation and give you a more vigorous foreign body response. So that's really important mechanistically. But also as we get that foreign body reaction, so the interruption of cellular communication, so that can prevent immune cells from being able to surveil for any damaged cells. But then also those cells that might be pre-neoplastic are walled off from the rest of the body as well during that latency period. Another contributing factor not related to the foreign body response to the material itself is viral contamination of the implant. So when we talked about sterility, we're mostly focusing on microbial sterility, right? But we could still have viral contamination. And you hopefully know that viruses can lead to cancer later on in life. So a good example of this would be HPV, human papillomavirus, has been linked to many, many cancers in humans. So if that's present on an implant, it could lead to cancer later on. So this figure shows graphically the process of the foreign body tumorigenesis. So here, we know when we have an implant, we're going to get the infiltration of the area as part of that inflammatory response by leukocytes. So we get our neutrophils, which are shown here. And then you get the monocytes, which turn into our macrophages. I'll abbreviate MAX here. And one of the interesting things about the neutrophils that we talked about before in terms of their normal activity is this respiratory burst. So that's one of the ways that they help clear out infectious organisms normally in an immune response. And so that respiratory burst involves the release of reactive oxygen species and reactive nitrogen species. And those are not really specific to killing any microbes necessarily. They can also have effects on the healthy cells in the tissue around the implant. And so here this labels them as being genotoxic, but those can be mutagenic. So we'll keep with that terminology. So they can lead to the formation of pre-neoplastic cells. Also during the foreign body response, we know we have the release of a lot of growth promoting factors, so a lot of growth factors that are leading to or stimulating proliferation of cells. And so that may potentially play a role. But here I want to focus on this respiratory burst because of the potential for mutagenicity. This table summarizes some results from the published literature on foreign body tumorigenesis in rats. And so here we can see a lot of different materials. So these are all polymers, so Dacron, nylon, cellophanes, which is a polyurethane, polyethylenes, etc. Many, many different polymers. And all of these have been noted to cause some tumorigenicity. And here you can pay attention to this latent period, so a number of days, we're talking about roughly 1 year and up in terms of that latent period, and this is in rats. And then you can focus here on the incidence, right? So the percent of the animals in these studies that developed tumors over time, and then this was in subcutaneous implantation specifically. And you can see really some pretty surprising numbers. So, I mean, a couple of studies here are up in the 45% range, so that's quite high. But even in the smaller ones, you know, it's around 10% or so of the animals that are developing tumors from these subcutaneously implanted materials. So this slide summarizes the timeline for foreign body tumorigenesis. So after implantation, we have our foreign body reaction. We have the cellular proliferation that's associated with all of that. And then, of course, there is the respiratory burst that's not shown here, but was on that previous slide. So this foreign body reaction leads to the development of these pre-neoplastic cells that I mentioned earlier. So they'll be present yet, but they haven't transformed into a malignancy. Then, after the fibrous capsule is fully generated, the inflammatory response resolves, the site becomes quiescent. But those pre-neoplastic cells are still in contact with the material, and they're walled off from the rest of the body. Or they can be if they're on the inside of that fibrous capsule. And this is the onset of this latent period. So then we can have a latency period that can last many, many years. And then at a later time, finally, for reasons unknown, there's this final maturation of those pre-neoplastic cells resulting in tumor growth. So the previous slide I showed you had numbers from studies on rats. In humans, there has really been a relatively low incidence of implant-related tumorigenicity, but it does occur. And so reasons for this, you know, may be because solubility of implant materials is low in physiologic solution, so concentrations may stay low below those threshold values for the initiation of that. But if the transformation does occur, it's still really pretty unclear, you know, what determines the length of this latent phase and what triggers that transformation. And there's also no solid correlation between, you know, different types of biomedical implants and tumor formation in humans. And this is really because the latent period can be so long. Nevertheless, it does occur. So I'm going to show you some data on that now. So this figure is showing an osteosarcoma. So that is a bone cancer. And so this was developed as a result of an orthopedic implant. So this was in a 68-year-old man, if you can read the caption. So a total hip replacement, one of our favorite orthopedic implants, right? And here you can see it in the radiograph here. So all of that around it. So that's all that osteosarcoma. And then you can really see it by gross observation here. So there's a large tumor that's formed around that implant where the bone is really just grown out of control. And then histologically, this is not at all what bone looks like. So it's very, very unhealthy looking, very neoplastic. So that was one example. Now this table summarizes some results from the literature on the incidence of this foreign body tumorigenicity in humans, the age of the patients, and then the latency period here. And you can see the types of implants as well. But here, takeaway point on this latency period, it's really, really long. So we see years in many cases. And you know, this one here, 36 years with this tibia pin and screw implant. Some of the other ones on the shorter end, you know, 1 to 2 years, but still quite long, you know, after implantation. This table is a prettier version of that previous one. It's a little bit updated, comes from a different source, but it actually has many of the same studies. But again, we're talking about a timeline of years post-implantation when this is being observed. It's not just orthopedic implants either, so we also see some vascular grafts and some heart valves as well in one study. So implant-associated tumorigenicity via the foreign body tumorigenicity mechanism is still a potential problem. So that wraps up this video on the problem as well as the mechanisms of implant-associated tumorigenesis. In the next video, we'll be talking about testing methods.